Okay, so when I was preparing this, I was a little taken aback because I realized a lot of what I'm going to talk about, Bert at least has seen. I don't know how other many people, but I thought, well, I'm going to focus on the people who may be newer to dementia research and my talks. Can everybody see? Can you guys see it? Okay, great. So I want to start by just introducing the idea of evidence triangulation. I don't know, we tried, this one doesn't work, so you have to, can you see, Bert?
I do.
Okay. So I want to introduce evidence triangulation and why, in particular, I've been really drawn to this kind of approach really throughout my career because I work on dementia and cognitive aging, and there are just a bunch of problems in dementia and cognitive aging that are methodologically disastrous. And so I think evidence triangulation can help us a little bit, being a little bit systematic about overcoming some of those problems. And I'll talk about a couple of examples. I actually think I'm not going to have time to do the evaluating medications, and it's not that new, but if people have questions, I'm happy to talk about it. And so I'll talk about causal effects of education, and my main example there is on dementia, but I thought it might be fun for people to see some of the recent COVID-19 results as well, just because they're cool. And then age when dementia-related processes first start influencing functioning. And then I'm going to talk about some pretty new stuff that's pretty half-baked, one might say, but I'm excited about. So I think there's several features of dementia as a clinical phenotype that actually defy efforts to identify its causes. So if you're interested in causal evaluation, causal determinants of dementia, there are many specific challenges. One is that dementia is actually a functional outcome that is caused by many diseases. So we define dementia as based on your functioning and impairments in functioning. But there are many different etiologic processes that can all drive those functional impairments. The other thing about dementia is that it has a very long, insidious development. It turns out it's not quite clear how long. However, there is really no study that looks at cognitive function at any age that doesn't predict dementia risk in late life. Going back to, I don't know the sequencing, but like Framingham, first found in middle age, cognition predicts late onset dementia. And then the nun study showed at like age 20, people's writing characteristics when they became nuns, that predicted dementia. And then the Scottish study showed at age 11, cognition predicted dementia. So really, there's no age at which we don't have stuff happening that is a potential confounder. And we don't know quite when the actual disease process begins. Because of that, it's very difficult to actually establish temporal order. We think of establishing temporal order as step one of causal inference, as showing that the exposures came before the outcome. But because we don't know when the outcome began, we can't actually easily show that this exposure came first. So these subtle cognitive and behavioral and physiologic changes emerge very slowly. And because it's a disease of your brain, it actually affects almost everything you could think of, right? This is a brain disease, so it's going to affect behaviors. It's going to affect how you interact with other people. It's going to affect your physiology. And there are numerous confounders across the life course that are all deeply socially patterned. So the key confounders are things like IQ, socioeconomic status. These are almost never well measured in data sets on older adults. One time I went through, there'd been like a recent review of major risk factors, and I went through every single one of them. Every single one of them, from hypertension, diabetes, to traumatic brain injury, showed a strong socioeconomic patterning. So there's no way to get around this. There's no easy way to get around this confounding. So this is why I'm interested in evidence triangulation. And Jamie just walked in the room, so I have to make fun of him a little bit so he can make fun of me later. Years ago, I said, we need to really find consistency across these different designs. And he said, foolish consistency is the hallmark of a narrow thinker. But I'm still arguing. I'm still making the argument. So the idea of evidence triangulation, I think the nicest description of this is from Debbie Lawler's paper in International Journal of Epi a few years ago, in which she describes strengthening causal inferences by integrating results from several different approaches, where each approach has different and assumed to be largely unrelated key sources of bias. Jeremy Lebrecq and Sonia Swanson have tried to be a little bit more formal about this, and I actually think their effort is quite nice and very helpful, even though they end up being narrower than what I think of as evidence triangulation. And they describe this as if we have multiple estimators, we apply both estimators to the same data and to the same research question. We would expect those estimators to agree when the causal assumptions are satisfied for both methods. And you have to choose estimators that, given substantive knowledge, they're expected to agree only if they're both unbiased, right? So that's their kind of definition of evidence triangulation. And I'll talk a little bit about, I think that's like the key insight there, but I still think it's a little bit narrow, and I'll talk about why I think it's a little bit narrow from how I hope we approach the dementia research. Is evidence triangulation new? Of course not. As I said, I've been arguing about this for a quarter century now. The premise of triangulation is not so different from Bradford Hill's consistency criterion. This is, of course, not what we mean by consistency in the causal inference language, but the classic Dahl-Hill criterion. This is a quote from the 1965 paper. The same results from precisely the same form of inquiry will not invariably greatly strengthen the original evidence. I would myself put a good deal of weight upon similar results reached in quite different ways. And at some point, I talked to one of my postdocs. She was like a first-year postdoc. And I was like, oh, this evidence triangulation thing is so cool. And she's like, you know, Maria, I don't think I understand it. Isn't this just like scientific thinking? And I was like, yeah, okay. It's just clear scientific thinking. So I think this is, but yet I feel that we often don't really bring this systematically into epidemiology, and especially in dementia epidemiology. I think there's been a lot of recent attention because, in fact, a lot of observational epidemiology has been absolutely dominated by variations on a single methodology. And that methodology is essentially covariate control or closing backdoor paths, fulfilling the backdoor criterion. Modern causal inference frameworks clarify the assumptions you need for causal inferences from any specific study, and they help you compare estimates from different studies and thus more systematically pursue evidence triangulation. I think the new, when I was a student, it was like you didn't really think about using multiple data sets together, but because it was so hard to get any data and the data sets were much smaller. Now I think there are really new data flows and much more heterogeneous data sources. There's much more commitment to data sharing. And I think that both the new data sources and the computational power offer opportunities for triangulation that can help us rule out alternatives. The evidence pyramid, which I still think really influences how people think about observational evidence, or about evidence in health research. I think it has really led to an oversimplification of causal inferences from the field as a whole, in the sense that we assume that if you go up the hierarchy, you somehow get better, without talking about how issues within the same study design can, there are weaknesses that are complementary, and you can draw on contrasting those complementary designs. So I think of all of the designs that we have as basically falling into one of three buckets. All of the designs for causal inference is basically falling into one of three buckets. One bucket is to fulfill the backdoor path criterion. Everybody has encountered the backdoor criterion, right? Essentially, we're assuming that you've got, if you're interested in the effect of X on Y, you've measured all of the paths, you've measured a variable along all the paths that are confounding that. The second kind of approach is to use an instrumental variable. Instrumental variables should be very familiar to everyone from the context of randomized controlled trials, right? We use randomized controlled trials. They're a great way to evaluate whether some treatment influences some outcome. And I think the big change that's happened in the last 20 years is that we see more and more in health research that we can use natural experiments as instrumental variables. We don't have to have just human-intended randomization. And the third approach is the front door criterion, which I would love to know if people have seen a good example of the front door criterion. I won't spend any time talking about it. I think it's super cool, but I can never make a compelling case about it, so I will just keep moving. So observational health research has really been dominated by methods that rely on fulfilling the backdoor criterion. Economists tend to lean on instrumental variables or some flavor of instrumental variables, where they find the core premise of the instrumental variables. You have some exogenous source of variation in your exposure that is not otherwise related to the outcome, to the potential outcome. Okay. This is probably right now one of the most influential figures in dementia research. It is the Lancet review of risk factors for dementia. And anybody who's up to date on dementia research will realize I'm showing you the 2020 version, not the 2024 version. It doesn't matter too much, except if you actually want to know the 2024 version. It looks really similar, but it doesn't fit on my slide as well. So, but they've added LDL and one other variable they've added, and so now for 4 years of progress. 4 years of progress, right? So the Lancet review is an incredibly influential review, and they update it every few years. One reason that it's incredibly influential is it's introduced the idea of population attributable fractions to dementia research, which I think was not at all familiar and is in fact really helpful and valuable. But they've gone through all these risk factors. This little homunculus-looking thing is the life course path. Starting from the upper green is early life, going down through late life. So early life, they say, oh, the PAF for low education is 7%, and then you go to hearing loss in midlife, alcohol use, depression, social isolation in late life, and you add them all up and you get 45% of potentially preventable cases. And it's a little bit more complicated than that, but not a lot more complicated. The evidence base for this review is almost all based on fulfilling the backdoor criterion. It is almost entirely based on covariate control. And almost all of those studies started when people were 50, 60, 70, and follow people up for incidence of dementia. That is the default study design. In some cases, for example, alcohol use, the effect of alcohol use on dementia, in fact, if you really drill down, so although they say alcohol use is bad, if you really drill down, they're in fact ignoring the contrast between moderate alcohol users and non-alcohol users. Because I think they don't like that result, because that result suggests that moderate alcohol drinkers have lower risk of dementia. So they actually report and estimate the PAF contrasting heavy alcohol users to moderate alcohol users, which the heavy alcohol users do worse, as in many studies, the simple observational analysis gives you a J-shaped curve. But I think that has such a public health problem to suggest that we should have moderate drinkers. When you read the report, you would actually just think drinking is bad. So I think, in fact, this research has relied very heavily on a particular design, and we all are so concerned about this design and the fallibility of this design that we actually don't believe our own results unless we like them. Unless we were already like, that's a nice public health idea. Have people play little brain games. That's a good idea. So manage hypertension. That's good advice. Nobody's going to be upset about that. But I think when it comes to something that we're actually troubled by, we don't really believe the design. So if we aim to move beyond confirming our prior assumptions and selectively adopting findings that we find appealing for other reasons, then we really need to start thinking about new design approaches. All right, I'm going to give just a very brief summary of some of the approaches. This is drawn from a paper led by Serena Gutierrez and senior authored by George J.B. Smith, in which we sort of went through trying to explain how you could think about evidence triangulation. Serena did a beautiful job, and I've condensed it to one slide with a lot of text. So, the first thing, evidence triangulation fundamentally rests on comparing different estimates of the same research question, right? That is the core tool. So to do that, what's our most common tool to compare results and to integrate results from multiple studies? Meta-analysis. Does meta-analysis help us with evidence triangulation? Not really. The premise of evidence triangulation is that all the studies are really similar, and so we can take a summary across all the studies. It helps rule out chance findings, but it doesn't really help rule out systematic biases in any of them. The meta-analyzed result is just about as strong as the underlying studies. So if they all have the same assumption, the meta-analyzed result has the same assumption. Meta-regression, in which you actually try to say what's the feature of the study that influences the effect estimates, there we can do some evidence triangulation where we can say, oh, all the results look different when you do this study design. But the really classic evidence triangulation tools are things like cross-context comparisons. The idea of cross-context comparisons is to take two settings where the confounding is expected to be completely different, where the confounding direction is expected to be completely different. The example I really love of this, which I think is Debbie Lawler's, but it might be George's, is with breastfeeding. So there's some settings where breastfeeding is associated with high SES moms, and there's some settings where breastfeeding is associated with low SES moms. If the association between breastfeeding and kids' health is basically about socioeconomic confounding, you would expect those patterns, those settings to produce different observational results. This is a place where I think that new data sources are really promising because we can actually draw on cross-national studies, for example, where there might be real differences in confounding structures. Like I recently saw a really beautiful paper on multilingualism showing that if this used in India, where multilingualism is very differently socially patterned across Indian states. The next category of approaches are based on instrumental variables. I am a big fan of instrumental variables. Most of what I'll show you is sort of my applied evidence is really drawing on some version of IV. This is both randomized controlled trials, but also Mendelian randomization, where we use genetic variants as instrumental variables, as natural experiments. I think have become very popular. It's a little odd to me the extent to which Mendelian randomization has become popular without similar adoption of policy IVs. Like very often, they're actually quite compelling policy IVs that we're not using as enthusiastically as genetic IVs. And then there are a set of approaches that are about bias demonstration and quantification. So positive and negative controls, evaluation of reverse causation. I'll show you an example with reverse Mendelian randomization, and quantitative bias analysis. All right. I want to talk about some examples now. Any questions before I go on? Okay. This is an example about the effects of education, and I'm going to talk both about dementia research, and then I'm going to do really quickly on COVID just because it's newer. And this really started from my dissertation. This is like, and I'll show you stuff that was published afterwards, but it's really the core of it was in my dissertation. So there is so much evidence that people with more education have lower dementia risk. It is observed in almost every setting. People with more education have lower dementia risk. And you can do meta-analysis after meta-analysis. This is a slightly old meta-analysis showing an overall effect estimate of 0.44. And all of these, there are other meta-analyses, they all show basically the same pattern. Nearly all the studies share the assumption of no confounding by prior cognition or parental socioeconomic status. To me, it is very difficult to imagine that cognition does not influence how much education people pursue, and that parental SES does not influence how much education people pursue. And these are, as I mentioned, these are strongly associated with dementia risk. So this is from Claudia Golden, who won the Nobel Prize for something else, but this was Claudia Golden's work on education policy. Claudia Golden and others showed that major changes in educational attainment across the United States in the first half of the 20th century were in part induced by changes in mandatory schooling. So as we increased the laws that said, oh, you can't wait till age 8 to start school, you have to start at age 7, or you have to start at age 6. You can't leave at age 12, you have to go through age 14, age 15. As we changed those laws, and nearly every US state did change the laws at least once, sometimes multiple times over the course of the century, we saw increases in educational attainment. This is a pattern. This is just the huge increases in high school graduation in the United States. This is the pattern in South Carolina by the birth cohort, and whether that birth cohort would have been affected, the mandatory schooling that would have been in place for that birth cohort had they been born in South Carolina. And you see that in the 20s, they went from 6 years to 8 years, and then they increased it to 9 years mandatory schooling. So if schooling, now not everybody is constrained by this. Some people were going to get more schooling anyway. Some people don't care what the laws say. But we have pretty good empirical evidence that a substantial fraction of people do increase their education based on these policies. So if schooling has an effect, we should see increases in cognition and reductions in dementia risk. And there are a few different papers I could have shown. I'm showing you work by Tu Nguyen, who's now on faculty at University of Maryland. There she is with her first child. And the reason I'm showing this is because she contrasts 3 different approaches. So she first looked at, this is data from the health and retirement study. So she first looked at, let's just control for confounders that we've measured, and showed that if you just control for confounders, you see a substantial reduction in risk of dementia, about a 2 percentage point decrease per additional year of school in the HRS sample. Then she used a genetic risk. So this is a few years old now. There's a genetic risk score that predicts education. I will say, as an aside, I actually hate this instrument, and I'm happy to talk to people about why I hate this instrument, but I think it's a really nice, like maybe you guys don't hate it, so you can believe, the results are all the same. So the genetic risk for education, if you do the IV analysis, that decreases. Each additional year of education predicted by the genetic variance decreases risk of dementia by 1.1 percentage points. And then you see this CSL, this compulsory schooling law. So each additional year of education induced by the compulsory schooling law, you see about a 10 percentage point decline in dementia risk. Now, I want to say this is too big to make sense, right? So they all have the same pattern, right? They're all showing pretty consistent results that education, whether you prefer a backdoor path approach or you want to use this genetic instrument or you want to use a policy instrument, you see the same pattern. But I want to flag that this is really large compared to what we would expect. Okay. So this is an example of, I think, a pretty useful approach where we're really contrasting these methods. They all have very different assumptions. You can critique any of them, but it's hard to critique them all and say, oh, they're all showing this thing that's not true. I want to show you another example with COVID-19 mortality, where we did something similar and it has sort of interesting somewhat implications. This is just the observational difference across the state of California from March of 2019 to February of 2021. 2021. This is the pandemic. And the colors are education level, and what you can see is a pretty clear educational gradient where people with less education have much higher COVID-related mortality. And you could see a similar thing with all-cause excess mortality, for example. Very strong association between education and mortality during the pandemic. Now, there are lots of reasons to think that this could be causal, but there's also reason to be skeptical if you're a skeptic. So it might be causal because education gets you better jobs. Education allows you to actually use information about how to stay safe. Education allows you to negotiate for safe working circumstances. But you might also think that education is confounded by all the other stuff that we think could be a problem. So this is work that's just, this is really work in progress, led by Whitney Wells, who's a UCSF PhD student. And I'm just going to show you one picture from this because they all look the same. But she is put on the x-axis here years of mandatory schooling. This is national mortality data. So she's taken all the deaths in the country for the first 2 years of the pandemic, and she's tied it to the US population information from the census, and then linked it back to the mandatory schooling for that birth year and birth state. So both the census and the death data have state of birth, so you can link that back. Everybody got the design? Okay. So she's linked to people who were required to attend 6 years, 7 years, 8 years, 9 years, 10 years, 11 years, 12 years of schooling. This is the odds ratio of COVID-19 mortality during the first year of the pandemic. So basically, if you were born in a place that required more schooling, it was very protective. This has nothing to do with your own education. This is about the policy that was in place the place you were born. Same thing in year 2. We had originally hypothesized that this would get stronger in year 2 as we learned more about how to protect yourself from COVID. But in fact, you can see they look almost identical. And in fact, when you look at pre-COVID, they look pretty similar. The absolute numbers are, of course, closer, but the relative pattern is pretty similar. And I will say also, just thinking about the dementia results, these coefficients are way too big for this to plausibly be about individual level education. There is something more than just individual level education that must explain this. Now, these results have state fixed effects. They have linear and quadratic trends for year of birth. They have some basic demographics to control for. And yeah, so I think those are very compelling, but there's this puzzle that we don't really understand the mechanism. So example 1, take-homes. Subsequent research has largely replicated the results for dementia. We've seen that in many other settings, in many other countries. Those results are pretty solid. There's some exceptions, but overall, that seems pretty compelling. The results for COVID are quite new. We haven't even submitted the paper yet, so we'll see what people say. There are questions remain about whether the education effect on dementia is really about changing what's happening in your brain or just making it really hard to diagnose dementia. So I think that's like, if you ask me honestly, what am I most worried about those results? I'm worried that it's not actually helping people in any substantive way. It's just making it really hard to diagnose because the number one thing you learn from schooling is to take tests. So it may just be that it's harder to see it. You can't say that with the mortality results, of course. I think that the policy-based IVs, and we see this in many other studies, the policy-based IV estimates are too big to make sense if there's a straight like educational attainment is the full mechanism that explains this. I think that there could be differences in educational quality that move with the compulsory schooling law. So we both, at the same time that states were investing in saying, okay, you have to stay in school longer, maybe they were hiring better teachers, they were teaching people who came out with better literacy and numeracy. I also think that there's something about potential spillovers, and especially for infectious disease, that we've never really dealt with this in education research. But like, we do know that your spouse's education affects your health. We do know that your community's education, and in COVID, we thought your community mattered a lot for whether you got COVID and died. So it may be that there really are spillovers, and the compulsory schooling law in particular would affect a whole community. So we would love to drill down into that, but we haven't yet. Okay. Any questions about that before I go to the second example?
So what do you think is causing this? I mean, what things would make you have a story that it's not just another year of education or something. So tell a story that would explain that big an effect in terms of different states. What happens to, people like in different,
Yeah.
that's all.
I mean, I'm not going to put my money on either of these stories. I think both are plausible and maybe both contribute. I think one story is, this comes up a lot with IV. The endogenous variable is mismeasured. It's something about education, but educational attainment as in years completed is just a terrible measure of what you get out of school, right? It's not measuring, like we'd really like to have literacy and numeracy, your capacity to use information, your capacity to trust the institutions, right? We never measure that. But maybe that all moves along with investments in schooling. It was very expensive to pass compulsory schooling laws, right? It was very expensive to say 14-year-olds, 15-year-olds, they could be working, they have to be in school. So states that did that cared a lot about investing in kids' education. So that's one story, is we've missed the latent construct in some important way. I think another story is that, in fact, if I happen to live in a place that changed the compulsory schooling law, it's very likely that my spouse lived in that place. So the extra education that I got because of that law, very likely my spouse got extra education. Potentially my kids got extra education. Probably my neighbors got extra education. And all of those things together could have economic implications that are much bigger than my own education. Whereas if you look at my own education, as like the conventional analysis is going to say, I'm going to contrast, you had 10 years of education, you had 9 years of education, and you miss all of that contextual effect. I think either of those are plausible, and I don't know. Yeah?
I mean, could some of it also simply be additional confounding by age, by state? I mean, I don't know what the specific analysis is. I don't think you could do this with HRS and dementia, but with the COVID data, couldn't you have large enough sample sizes just to look at 2 adjacent years, those who were and were not subject to compulsory education, and then you have more like a regression discontinuity design. If you're just looking at those 2 years of birth within state, and again, I think you'd have a large enough but sample size to do this, and I would find it a lot more
convincing if we looked at so we can definitely do it. I think the results overall have been fairly robust to different specifications, but and I think the issue with the interrupted time series is the regression discontinuity is you have in the United States compulsory schooling laws are not very well enforced. So we'll have 15% of the sample, for example, who got an extra year of schooling. So you see very small effects within any given space. So you kind of want to combine those estimates, which is what the fixed effects approach is intended to do. But we should try to poke more holes in it. I'm very open to,
So one clarification, because I don't think I understood the analysis for the compulsory school in the States have been, if anything, going up, right?
Yeah.
So those born many years ago, therefore older by COVID, are going to be in the first 6 years and so forth. So how did you account for age in that analysis?
So effectively, age and birth year are collinear, right? So we've controlled for birth year so that's effectively collinear. And yeah.
All right.
Yeah.
that I think a lot of the times when you kind of colloquially say what the causal question is, it sounds like you're asking the same question across all of these different approaches. But if you actually drill down to what are you really estimating, like the causal estimate that you get from a confounding adjustment approach versus an MR approach versus your policy IV approach, you're actually targeting something slightly different. And I think a lot of the times what I hear a lot of people say is, oh, I got the same answer, so my triangulation was successful. Or if they found different results, they say, oh, well, I was actually targeting different things, and that explains why I'm getting different results, right? So how do you, like, a priori decide what differences in the definition of those estimates are meaningful so that you're not making that conclusion after you see those findings?
Absolutely. Okay. Let me go through. So we did this as part of a grant on evidence triangulation. I'm going to walk through these steps, this is also not published, but so I'm glad you asked the question. But we see this in dementia research all the time, like with the contrasting trials and observational evidence, where we intervene to manage diabetes, and we manage it very carefully for 18 months, and then we didn't see a difference in dementia. But how do you compare that with observational results where people have had diabetes forever? So we sort of went through these steps that you want to try to do. First, say, is this the same causal and the same statistical estimand? Is this the same exposure definition? And some of these, if they're not, you can convert, right? You can go from one to the other, right? You can say, okay, how do we get back to this? Is this the same exposure definition? Is this the same outcome definition? Are these the same populations? Do you need to do some kind of transportability or something? And then if you think that these are all the same, can you combine results or compare results, right? And I think very often what we see is people are saying, oh, it's a different estimand. I'm really uncomfortable comparing them because it's a different estimand. It's like, they should both be beneficial. They should have the same sign. You can actually get a certain, like, you don't have to just give up and walk away because there's a subtle difference. And I think I think we need to be at a place where you can say, well, how much would those estimands plausibly differ if we see this? So I think you just have to be systematic about when you're comparing them. And it's obviously a fair amount of work, like just things like getting the exposure definitions to be consistent. I can talk about that quickly, is a major challenge. So. All right, we have like 15 more minutes. Okay, I'll do one more. Do one more example with the BMI. Okay. This is a different type of question in that what we're really interested in is at what age do dementia-related diseases begin to influence physiology? Now, this is an important problem because if you think we're going to do prevention, you might want to say that we're starting before there's already physiologic manifestations of the disease. And if you want to say that you're drawing causal inferences about social isolation or brain games and dementia risk, you might want to say, I looked at people's isolation level before the disease had started. So I also think this is an important question because of our story about the etiology of dementia, which really begins with amyloid deposition. But if you think about amyloid imaging in living adults, it began in around 2004, 2000, somewhere like. So we actually haven't had amyloid imaging for as long as we think the disease might take to develop. So there's no longitudinal natural history studies with repeated amyloid imaging because it just hasn't been around that long. So I think it's helpful to understand, are we really studying this from the beginning? Conventional approaches to try to understand when does the disease begin conflate factors that are early indicators and manifestations of disease from factors that are actually influencing disease. Right? So if you're interested in when does the disease really begin, you need to disentangle, does this thing cause the disease, right? Or is this actually an early manifestation? And so if you think about the Scottish children's study, Scottish age 11 study, I think it was called, I actually don't think the age 11 cognitive scores are an indicator of early progression of dementia. I think the age 11 cognitive scores are predicting who gets diagnosed with dementia because it makes them more vulnerable. Right? Okay, so this is all work from Willa Brinowitz, who's at Kaiser in Portland, Scott Zimmerman, Peter Butow, and Min Choi, who are all analysts on my team, fantastic analysts. Okay. So the approach here, we want to know at what age does preclinical dementia begin to influence physiology, behavior, and we don't have a measure of preclinical dementia, but we do know that preclinical dementia causes weight loss. This is an established phenomenon that people lose weight as Alzheimer's approaches. So maybe we can just look at when does weight loss begin for people who develop dementia later. The problem with that is that elevated BMI causes dementia, we think. So it is certainly a very strong risk factor for dementia. So you've got these two phenomena going on at the same time in midlife, where high BMI is increasing risk of dementia, and maybe weight loss is reflecting early development of dementia. So the idea of the study design is to look at the Alzheimer's disease genetic risk score, so to take a polygenic score that we know causes Alzheimer's disease and therefore dementia, and try to understand at what age can we first detect an association between that genetic risk score and weight loss. Okay. And the Alzheimer's disease genetic risk isn't vulnerable to this BMI confounding. So if we expect the AD genetic risk scores to be not associated with BMI at ages before dementia begins to cause weight loss, but to become associated with BMI at ages after dementia begins to cause weight loss. Okay? Everybody got that design? Premise? Okay. We started doing this in UK Biobank. The main advantage of this is sample size. There are also lots of limitations of this. So there are about 400,000 people, ages 40 to 69. This is cross-sectional, so we're going to pretend this is longitudinal, but it's really cross-sectional, just so you know what we're doing here. We created an AD genetic risk score. I think then we used the most recent meta-analysis, or meta-analyzed GWAS, which was like the Lambert scores, or however you say their name, and including ApoE scores. We used BMI, measured at study enrollment, and we estimated a linear regression where the dependent variable is BMI, and we predict that with age squared. So that's kind of age and age squared kind of describe the typical life course development of BMI. People gain weight until middle age, they start to lose weight. And interactions with the Alzheimer's disease genetic risk score. And we've kind of refined this approach. I'll show you some results that use, basically we look across all possible cut points to find the best fitting model for all possible cut points when we sort of have a thresholding, so there's an age at which the interaction becomes active and allows the BMI slope to change over time. And then what I'm going to show you is predicting out curves of BMI predicted for people at the highest and the lowest Alzheimer's disease genetic risk. And so this is, the age is on the x-axis. The red is the 10th percentile lowest Alzheimer's disease genetic risk, and the black dots are the highest AD genetic risk score. And what you can see is that basically in people's late 40s, that's the best fitting point of divergence. Now, this isn't statistically significant until a few years later, but if you fit those curves, because we don't think that there's a sudden change, we think this is a slowly accumulating biological process. If you fit those curves, you see late 40s is the point of divergence. We've repeated that with, so we thought BMI is like a really random place to start. So we're going to try other indicators that maybe are more clearly linked to dementia, because a lot of the first feedback, including I think from Bert, was like, I don't know, maybe the genetic risk influences BMI directly. It's not about dementia per se. It's not about Alzheimer's. And so we also did this with the cognitive assessments in UK Biobank. So UK Biobank has this like deluge of cognitive assessments that all have different sample sizes because they like phased in and phased out. So we have this bunch of cognitive assessments. And we basically went through every cognitive assessment to see if there was evidence of an interaction, and then we checked for where there was the best fitting age of divergence. So at what age was there evidence that the AD genetic risk score became associated with, so all those cognitions show decline in older people. So at what age is the best fitting point where the genetic risk score starts to predict faster decline? And I'll show you that picture. So that's this picture. The blue lines are the best fitting point of divergence. The red lines are this age when they're statistically significantly divergent. So the difference between the high and low is you can actually detect it with a statistical significance test. What you can see is that by age 50, you're starting to see a lot of divergence. We show the same thing with the MRI samples. So they have a brain MRIs. In UK Biobank, the sample's much smaller. I think it was about 40,000 people at that point. But you can see the same patterns where in the orbitofrontal cortex, hippocampus, thalamus, amygdala, places that we actually do think are associated with Alzheimer's, you see the same pattern where the ADGRS becomes associated with this at a particular age. I was really worried about these results because of the UK Biobank sample. So the UK Biobank, for people who know it, it's just like the sampling is puzzling. And so I thought we could have, this could just be a fluke of how they enrolled people. Like maybe this 50-year-olds with the skinny 50-year-olds with dementia were all wanted to participate, something. You know, it's too complicated to even come up with a story. It was just a worry. So we're starting to do this in the All of Us data. Also, really weird sampling, but different. And this is our first effort at this, which is using BMI because we don't have brain MRIs in All of Us. And what you see, there we do have repeated measures of BMI, so it's pulling from EHRs. And so we have about 200,000 people and about 2.5 million observations. And we see the best fitting point of divergence at about age 51. So suggesting something not great is happening. I think overall these suggest Alzheimer's disease-related changes in BMI, cognition, and brain MRI measures beginning to emerge in people's late 40s and early 50s. There is, I don't love these samples. We need really big samples. So if anybody has a few 100,000 people that they have brain MRIs on, let me know. I want to do this. Yeah, if you have a nationally represented cohort with 200,000 people with MRIs, that would be perfect. All right. Oh, that's promising. Okay. The changes could be attributable to pleiotropic effects of genetic variants. We can't necessarily rule that out. It seems like it's increasingly bending over backwards to come up with an alternative when the story that there's a long etiologic period here seems pretty plausible. But the implication is that Alzheimer's research beginning at age 65 is probably 20 years too late to be for primary prevention, and risk factor associations for measures in middle age or later potentially confounded by emerging diseases. All right, I showed you this. Anybody have any questions about that before I go on to the last few slides? Are really, yeah, yeah.
So you use the genetic score.
Yeah.
But this is, if you put in ApoE, it's overwhelmingly a matter of ApoE in there. So is this not all what you see, a relationship between ApoE and...
We do it with and without ApoE, and it is much weaker without ApoE, but you see the same pattern. And I don't...
Same ages also?
Yeah, it's just noisy. And it, like we've done this with the Lambert score, the Kunkel score, the Bilingua score, you know. And there's like, sometimes it's 53, and sometimes it's 47, but you see pretty, and I don't think the method is really can say it's like 48.5, but I do think that it's pretty compelling that it's early middle age. Yeah.
So my understanding, you're essentially using genetic risk for Alzheimer's sort of similarly to an instrument here, but my understanding of most genetic studies of Alzheimer's disease is that they're sort of case controls that are done in quite late life.
Mm-hmm.
So they're necessarily subject to this really heavy competing risk, like even ApoE
Yeah.
also operates this way, right, where it's so strongly related to cholesterol, that's like very heavily related to death from cardiovascular.
Yep.
How do you, and all of these things that you've described also potentially have an impact on your survival, right? BMI, education.
Yep.
So how do you determine whether, like, how do you choose an appropriate instrument given that the GWASs are so heavily impacted by competing risk and very rarely sort of account for that?
Well, so I totally agree with your critique of the GWASs. I will say that I think that despite the limitations of the GWASs, they predict really strongly, now largely because of ApoE, but you put all those things, even without ApoE, you put those things together, in almost any setting, in almost any cognitive outcome, you see this pattern. But we haven't tried to like actually quantify how that could work. So walk me through, like, how do you think that could work? That really the ADGRS is associated with...
So my concern is that most of these genetic associations with Alzheimer's disease are potentially driven by the effect of those genetic variants on risk of death. And that it's really a selection bias pathway happening. That's potentially, as you say, physiological relations that accrue all of these other things. Because as we know, there's a lot of different causes of are really mapping to these like what you found, these selection bias pathways that you found through these others.
Yeah, I think that, I mean, let's think about how we could actually test that. So even though I wrote my dissertation on collider bias as like a major form of bias, in reality, I think that the magnitude of selection bias is often not that big. And the causal structure has to be pretty complicated with important interactions. And I think Miguel's shown with smoking, for example, there's a case where I think this is a pretty compelling case that there's some survival bias. But I think it's worth trying to figure out if we can actually quantify that bias. And I guess the other question is like what's real, like you'd have to actually be pretty specific about why you think the BMI is causing mortality and that's inducing an age-specific association. So I think it's plausible. I wouldn't put my money there, but it's worth trying to explore. Yeah. Okay. We have a few more minutes. Okay. All right, I just want to mention a few things that are really developing. This is partly so I can try to get Jamie to explain how to do this to me. So this is like, I've got him as a captive audience. One of the issues that you raised was if you have a different exposure measure across different settings. So if you want to contrast studies, you have a different exposure measure. And those are, then it's really hard to actually figure out how do you actually integrate the evidence. So alcohol use is an example where people have, lots of studies have different measures of alcohol use. It's like very easy to ask people to self-report, but they have slightly different questions. This study asks, like, what's a 90-day look back? And the study asks for a 30-day look back period. That has been a real challenge for us when we wanted to do evidence triangulation across these study designs. And so what we've tried to do, and this is still like not done, but what we tried to do is what we realized is like, you don't actually need the information about the crosswalk between the measures in the same data set where you have the outcomes. You actually can get the crosswalk across the measures in a different data set and then just have the crosswalk that you apply in the data sets where you have the outcomes. And it's pretty cheap to do new surveys on people that are not well characterized. So this is an online panel, this Qualtrics panel, for basically $10 a person. You can give a 20-minute survey, and you can get the data in weeks. And they'll give you back some basic demographics and some target demographics. And then you can estimate, you can actually show people both versions of the questions and get a crosswalk between them. So that's the premise of our approach. So we're interested in the effect of alcohol use on general health. Sorry, our DAG is going the wrong direction. And the idea is there are 3 different measures of alcohol use, and we're going to use these 3 different measures to get at the latent variable of true alcohol use. And then across different studies, get an association between this latent variable. That actually, like the data collection, went really smoothly. No problem with the data collection. Highly recommend for that. There were some issues in that we also could randomize the order. Like it's easy to randomize the order so you can test for things like sequencing order effects and so forth. There have been 2 issues that we're really concerned about. One is that people answer really quickly. So we think that there's some just trash answers, and we're trying to figure out how to rule out the trash answers. It's not just speed. Like there's some things that are totally internally inconsistent, and I'll show you here. This is an example between 2 questions. This is the HRS version of an alcohol quantity question and the NLSY. And you can see these are associated, but it's not like super strongly associated, you know? And so we can get those stronger if we throw out people with absurd, inconsistent responses on various questions, but it's still a concern. And then we're implementing this latent variable model to estimate the effects. And then I don't think we really have time. This is Erin Ferguson, is this amazing PhD student who's done this multiverse analysis. And every dot here is a different analysis, where she has cycled over every possible covariate combination, specification of the sample, run-in period, all these features of the design. She has cycled through them. This is the Kaiser Northern California. This is their main electronic health record data. This is their survey data, and that's their genetic data. She's gone through, so we have genetic covariates to control for, and she's gone through every single variation to look at the distribution of effect estimates across all of those decisions that feel a little bit arbitrary. And This has been incredible, like incredibly nice coding to get it done. And what she can say is like, oh, it really matters whether you have a run-in period. It really matters whether you adjust for these 3 clinical covariates. Nothing else matters. Education didn't matter. Like diabetes, hypertension, depression. I think those are, yeah. And then you can come down to, okay, this is kind of the distribution across reasonable choices. And it's, 1.0 to 1.1. This is the exposure here is statin initiations, emulated trial design, statin initiation, incident dementia in the Kaiser data. So we weren't confident about our results, and now we think it's somewhere in there. Yeah. Okay, I will stop there and just say, still, there's a lot of attitude of like, you should just get the answer. Don't try all these different things. Some of our co-authors are like, no, just give us 1 point. I think that there's a real sea change about being willing to actually try with the risk of finding something that you didn't expect. And I'll just stop by thanking my amazing group.